Hello, I'm Chao-Hong. In this talk, I will talk about computational interpretation of complex categories. This is a joint work with Sabry. Complex category has a lot of application in computer science. For example, it is used to model linear logic, concurrency, and quantum computing. So in this talk, we will focus on the operational semantics for complex category. First, let's revisit the definition of complex category. A complex category is a symmetric monoidal category where every object has duals, and there is also morphisms eta and epsilon, which satisfy the snake diagram. The snake diagram states that if you compose eta and epsilon in a leg way, it is equivalent to ID, and if you do the same for epsilon and eta, it's also equivalent to ID. And the focus of this work is the operational semantics for complex category with conventional sum types and conventional product types. Our starting point is a reversible programming language Pi. Pi has empty type, unit type, and sum type and product types. And the combinators of Pi are type isomorphisms, which are found by monoidal category. So let's look at the combinators of Pi. First, these are the combinators from the definition of category. So we have ID and we have this composition. And then these are the combinators from the monoidal category of sum types. So we have this swap, a sock, and then these are from the functor law. And similar for the product types. And in the end, we also have these two rules from bimonoidal category. Putting all this together, we have a bimonoidal groupoid. So Pi basically provides the minimum requirement for what we need to do for our development. The operational semantics of Pi, we will use evaluation context. So there are two types of state, enter state and return state. And every state have a combinator and a value and a context. So these are the rules for ID. So ID does nothing and returns the value immediately. And for composition, we first evaluate C1, and then when it is done, we evaluate C2. And then when C2 is done, we return the value as the results of C1 compose C2. And these are the rules for the sum types related combinators. So these are all performing permutations on sum types in the straightforward way. And in here, we just call C1 and C2 depends on the inputs. And for product types, this is also intuitive. And for C1 times C2, we first evaluate C1 on X. And when it's done, we evaluate C2 on Y. And then we return the whole results. And for the combinators from bimonoidal category, we are just performing the straightforward permutations on those types. And to define the evaluation, we just define it as we use C1 on V1 with empty context, and then in the return state, the V2 is the result of this evaluation. And since Pi is a reversible language, we can also define this backward evaluation. So in here, we just use this relation, which is the inverse transition relation. So, and we can prove that these two are inverse of each other. So Pi is actually reversible. So let's look at some example of Pi. First, we can represent Boolean value using this 1 plus 1. And then we can using a swap to perform this NOT operations. So this is straightforward. So when we have a false value and we do this swap and then it becomes true. Now let's look at a little complicated example. So here we are trying to write this CNOT. So the first step of this CNOT is distribute on the first value. So if the inputs are both false, then it will go to the upper branch and then it does nothing and then return the result, which is still false and false. But if the first value is true, then it will go to the lower branch and then it will perform this NOT on the Boolean. And then it returns the result. So we have true and true. And then using this structure, we iterate this structure again, we can obtain tuple get. And since tuple get is a universal reversible logic get, so every Boolean function can be computed using tuple get with NCR wire. So even so, Pi looks like a very simple language, but it's quite powerful, and just a small fraction of it can basically compute every Boolean function. Our goal is to extend the bimonoidal structure of Pi to complex categories. So we will extend the monoidal structure of some types to a complex category by adding negative types, and we will try to extend the multiplicative monoidal structure in Pi to a complex category by adding fractional types. And in the end, we will put two things together and resulting in a language which has both negatives and fractionals. Before we proceed to talk about the operational semantics of negative and fractional, we first think about what does this isomorphism means? So if you think about it using this cardinality viewpoint, you will see that the counting does not add up. So this negative and this fractional must represent some kinds of effect. But what kinds of effect about this? So let's to think about this, so let's consider a very simple example. If we want to represent n elements, using some type, we can represent it using n unit type sums together. And for the same thing, in product type, we can use the Booleans. So we only need log n Booleans. And in general, every operations working on this sum type representation takes linear time, but we only need constant memory, which means that we only need one slot. But for this product type, we need log n memory because they are log n values, and usually our operation takes log n time. So this suggests that the duals of some type should represent some kinds of effects on time, and the duals of product types represent some kinds of effect on space. Okay, so let's think about how negative types work first. So our goal is to satisfy this diagram. Now let's look at the epsilon first. So epsilon can only run in forward directions because of its type. There is no inhabitant of entry type. And all you can do is to turn the execution directions to backward because you can never come up with an inhabitant of entry types. Similarly, for eta, it can only run in backward directions because you don't have inhabitant of entry types, and all you can do is turn the execution direction to forward. So combine these two things together, we can satisfy this snake diagram. So this A comes to here, and then it turns around, and then it turns around again, and it will end up have the same value. So in a type system, we just add a new negative types, and the value of negative type is just a normal value with a flag which indicates that this is going backward. And for the machine semantics, we need to add a direction flag for each state because now we can either go forward or backward. And the forward rules are still the same as pi, and the backward rules are the inverse of pi's transition relation. And epsilon and eta just turns around the evaluation here and here. Now let's think about evaluation. So since now we can go in forward and backward, and the resulting state can also have a forward state or backward state. So now we need to deal with this two possibility of initial state and two possibility of the terminal state. So in here, we use this composite set, which has a union of A in the forward direction and a value of B in the backward direction. So the differential evaluation is like this. So if we have a combinators from types A to B, then it goes from the forward A, backward B to forward B and backward A. Now there's one thing we need to think about is this function a total function? So the evaluation of pi is very simple and it's straightforward to prove that it is terminating for every computation. But now we can go back and forth. Is not really, we don't really sure about what really happened when we add these effects. Now the answer is yes, but how to prove it? So intuitively, we want to prove it by induction, but then we encounter this case, which is the composition. So as you can see in the figure, the information flow is like this. So it's possible that the execution can bounce in back and forth between C1 and C2 and never stop. And the induction does not quite help here. So let's take a step back and think about something more fundamental. Now, the machine we are defining is a reversible machine. So first, let's revisit the definition of reversible machine. So a reversible machine is a set of machine state and a transition relation, which is forward deterministic and backward deterministic. Now, there's a simple lemma for reversible machine, which is non-repeating lemma. It says that if S0 is an initial state, which means there does not exist any states go to S0. Then if you start from this state, you can never take repeating steps. So using this non-repeating lemma, and then the fact that the reachable states are always finite in our semantics because the combinators has finite size, and then the contexts are just a decomposition of the combinator. So it also has only finite amount of possibility. And since we only have finite types, so the value part is also finite. So the whole reachable state is finite. That means that every execution is terminating, and this is indeed a total function. And similarly, we can also define this inverse evaluation, and we can prove that they are actually inverse of each other. So this is actually reversible. And we also prove that this is actually a compact curse category. And more is also an inverse category. And we also have an interpreter implementation, which use exception handler. I won't discuss it here, but the detail is in the paper. Adding negative types allows us to define a lot of interesting combinator, which gives us some kinds of higher order behavior like curry. And most importantly, it allows us to define trace. So trace let us doing this iterative computation of this F. So we can compute this F a lot of times, and if you is actually equivalent to this because we just proved that every execution is terminating. So every trace can be turned into a circuit like this in pi, and you only need finite amount of copies. So the two functions will end up be equivalent. And using trace, we can just write down a circuit for loop. So this for loop, if the inputs are all false, it will compute like this for loop. And of course, as I just said, we can decompose this into a pi program, but then we will need to have an exponential number of copies of that. Now let's think about fractional types. So our goal is to satisfy this diagram. Now for epsilon, it takes GC tokens and collects a value of type A and deallocate the space of both of them. And epsilon creates a space and a corresponding GC token of these fractional types. But now, which value should we create? So that's the problem. And there are two problems in this setting. The first one is which value should eta create so that A and A prime in this diagram synchronized. And we also need to deal with this 1/0 problems. Otherwise, we will get a combinator which is from unit types to empty type, which does not make any sense at all. So our solution is we move to pointed fractional types. So now the eta and epsilon are indexed by a value of type A, not just a type. And the same for epsilon. And this is 1 over this smaller a here, not just this a. So now eta knows which value to create. So it's just this one. And it also creates this GC token has 1/a. And epsilon now need to do a little extra work before garbage collecting both of them. So it need to check that either A and A prime are the same or not. And if it's not, then it will throw exception. So for the type system, we now add this pointed version of fractional types. And the inhabitant of this fractional type is just a token. Since it does not contain any information because the information is already in the type. And for the machine semantics, now we need to add a failure state because now computation might fail. So the transition, we still have all the transition rule from pi, and eta just creates the value in its index. And epsilon need to check if these two values match. So the evaluation also need to change a little because now we can fail. So if it goes to the failure state, we just return 0. And it's straightforward to prove that it's terminating because we just add in the possibility that it might fail. So it either gets a result or throws 0. And similarly, we can define the inverse evaluation, and we can also show that they are inverse of each other. So this is still reversible, but now it's like partially reversible because this is a partial function now. We have an interpreter implementation using maybe monad, which I will not discuss here. Please read the paper. So now for the category constructions, now we need to use pointed type here. And we show that this pointed type category is indeed a compact closed category, or more, it's a compact closed grouper. And this allows us to define some kinds of like partial application things in using fractional types. And most importantly, we have trace. So trace here is like a scope allocation mechanism. So it basically, in this scope, you can use a value which has, you can use this value C, and when you are done, you need to return it back, and if we reset to C, otherwise it will throw the exception. So using this trace, we can reproduce the construction in Tafri's paper. So in here, we can use 3 Tafri gates to construct a 4-bit Tafri gate using trace. Now we have all the pieces. Now we want to put it all together. So we have this new language, which is PyQ, which has this negative types and this pointed fractional types. And their values are the same as defined before. And the machine states now have the directions and also have the failure state. And the transition rules are basically all the rules we have discussed in combine. And then we have these 3 additional rules to handle the backward direction for fractional types. And the evaluation is similar, but now it could return error if it goes to fail state. And we can still prove that it's terminating. And we can define the backward evaluations, and it's still reversible. And we also have interpreters using mapping monad and its session handler in combine. Now in this language, we can write down a lot of combinators based on arithmetics on rational numbers. Like, if you negative and negative, you get back to the sense, and you can distribute things like that. As an example to demonstrate the expressiveness of PyQ, we implement a set subber. So this set subber uses 2 trace from both negative and fractional. So this loop uses trace for negatives, and in here we use the trace from fractional to create enough fresh false value and zero value so that we can produce the results we want. So if this circuit is satisfiable, then the execution will succeed. But if this circuit is not satisfiable, the execution of this circuit will throw exception. Now, to summary, in the paper, we have abstract machine semantics for both negative and fractionals, and also PyQ, and we have interpreters for 3 of them. And we prove a lot of meta-theorems for these 3 semantics. And we also have construction of complex category for fractional and negatives. And we also have a full implementation of set subbers, and all the work is formalized in Agda. So if you are interested, please read the paper and play with the Agda code in the artifact. Thank you.